Good morning, ladies and gentlemen. I'm a co-session chair of this ACI, JCI joint seminar on the advancing the design of concrete structures. And this is a continuous session and part 3 of the 4 sessions. This is a session guideline. Please please set all cell phones to silent or vibrate. Recording of session is not allowed unless specifically approved in advance by ACI and speakers. The information presented represents the view and recommendation of the individual speakers and does not necessarily represent the view of ACI or its committees. The audience is expected to exercise judgment as to the appropriate application of the information. And I'm a professor of the University of Tokyo, and I teach the structural analysis class, and yes, of course, I'm engineering professor. And the other moderator is Michael Brown. Could you introduce yourself?
Yeah, so Professor Shihara from Tokyo, and I'm Michael Brown. I'm with Jenny Elsner, and so it's a pleasure to present this part 3 of the joint JCI ACI symposium. This is, I think, the 6th one of these that we've done, so it's very nice to be able to continue this tradition. I'm going to let you continue.
Okay, thank you. I also thank all of you to attend this session. To the beginning of this session, I'd like to tell you a very short old story I remember as a connection of Japan and U.S. In 1890, in the Golden Gate Park, west of this downtown, they are constructed a new observatory. It is called Spinny Observatory, made of the reinforced concrete. At the top of the hill, it is called now Strawberry Hill. But in 1906, a great San Francisco earthquake happened, and the downtown area destroyed and burned out, and also the reinforced concrete structure there at the top of a hill torn down perfectly. In the downtown San Francisco, some very high-rise buildings still remain intact because they developed some empirical seismic design at the time, and they use a steel frame and encased with the brick masonry. Some of the building is the Westin Hotel facing to the Union Square, the Westin Hotel. And the building in downtown San Francisco was not constructed reinforced concrete because the Union protected brick press workers because reinforced concrete building eliminated. So the very few structure was constructed using reinforced concrete. But exception is that observatory building at the top of the hill because very far from the downtown. And after the earthquake, 2 big name professor came from Tokyo to reconnaissance. And one of them are Professor Sano Riki. He's an architecture, but strongly have interested in the structure design. And it is a famous story to Japanese. He saw the Spinny Observatory building there and find it is fireproof and have a very good ductility of the building. Even if the ground is broken, but it stands still. But it seems in San Francisco that the notorious story that Mr. Spinney donated the building to San Francisco, and he insisted to put the name of him to the building. At the time, he was not welcomed, and that new building is very good place to command the view of Pacific and downtown, but torn down by the San Francisco earthquake just 15 years after of the construction. But to the Japanese, the professor sees the damage and go back to Japan, and Professor Sano became an advocate of the reinforced concrete structure. And after 20 years after, the great Kanto earthquake happens in Tokyo, and more than 500 buildings was constructed by using the reinforced concrete at the time, and it is very good performance. So this is very interesting mysterious link between San Francisco and Japan, as well as concrete. So this is a very interesting story, and if you have the interest, maybe there are good resources in the internet about this story. I'd like to read it and strengthen the tie of Japan and the United States again. Thank you very much. And I use much time on this subject, so I'd like to introduce the first speaker, Professor Nishiyama. Okay, he's a professor of the Department of Architecture and Architectural Engineering of the Kyoto University. He's also currently the president of the Japan Concrete Institute. And he receives the doctoral engineering degree from the Kyoto University. His recent research is including the shear wall test presented today, as well as research on the soft first-story building damaged by the 2016 Kumamoto earthquake, and research on the steel for reinforcement, partially strengthened by the induction heating, as well as he carried out research on the RC columns with wing walls, and research on precast concrete columns assembled by unbounded pre-stressing bar. So thank you. So I asked, please start the presentation.
Why don't we start with, before we get the presentation, let's go ahead and get the first code.
Yes.
Yeah, because some people want to get PDHs, right? So let's make sure we've done that. Okay, there's a little bit more information about how you redeem the codes, so you can go onto the website, my ACI, and then some information about the learning units. So this course would offer 2 learning units. Oh, sorry, I thought that was presenting. Hold on. Hold on.
Click here.
Yeah. No. Where's the mouse? Here, it's good. Okay, so, yeah, so you can go onto the My ACI for the PDHs on concrete.org to redeem those. And you, like I was saying, it's good for 2 learning units according to AIA and CES criteria. We'd like to recognize the sponsors for this session. Okay, we have a few learning objectives, particularly about shear wall behavior, double hook fibers, image analysis for RC columns, and then performance-based codes for foundation performance. Very good. All right. Thank you.
So, good morning, everyone. My name is Nishiyama, and then you can see here the first author or the leading researcher of this project is Mr. Ryo Yamada but he couldn't make it. So then instead of him, I will present this project to you. So then the second author, the Professor Masanori Tani, he is an associate professor of our lab, and myself. So what I did in this project was to write the proposal and obtain the money. Okay? So then anyway, next. So these are the contents of my presentation, and then you can see here we have the paper, the same title of this presentation in the ACI Structure Journal last year. So then if you are interested in this project, so you can have the paper, you can have a look at the paper. Okay. So the first introduction. So several years ago, we conducted a shaking table test in E-defense. Probably you know what the E-defense is. So then this is one of the biggest shaking table facility in the world. And then there we constructed a 6-story, 30% scale reinforced concrete building. Then we applied the shaking to this building. So let me show you the short video where. So how we are. Here. So we applied a earthquake record recorded in during the Kobe earthquake in 1995, and then during the shaking, we observed this type of failure of the walls, right? So then the wall failed differently or different from what we expected. So then so of course those walls failed in shear, but we had seen the slippage at the bottom of the wall. So then after this shaking table test, we found that the boundary condition or forces around the wall should be considered. So then this is a schematic figure of the wall, and then this is the main direction of the wall. We call in-plane direction, and then the out-of-plane direction we usually have the beams, and then from those other shear force of the beams, this wall has a axial force, and of course as the earthquake load applied to in this direction, the axial load on this wall varies. And but in Japan, we usually use this design equation for design the walls. So at present, structural performance evaluation method of RC members considering tri-directional forces in earthquakes has yet to be established. You can see here this is a concrete contribution and the shear reinforcement contribution, or horizontal and vertical reinforcement contribution. And then also here you can see the contribution of the axial force. So then the, but we don't know how much axial force, or we don't know how this axial force have an effect on the shear behavior of the wall. So then the objectives of this project is investigating the effects of axial load condition and the lateral bidirectional loading path on the shear capacity of shear walls. And then we conducted the loading tests on shear wall specimens subjected to bidirectional loading under various axial load. So the first, the outline of experiment. This is the specimen which we used in this project. This is a 30% scale shear wall with. So we constructed the several specimens, and they were identical. They were identical, so that they have the same dimensions and the same reinforcing arrangements. And then this project started several years ago, and then we constructed several specimens. So then but today I want to focus on these 4 specimens. And then you can see here the experimental parameters as the axial load, and then the out of plane, and then the in plane drift ratio. So this is a ratio. Here you can see. Here you can see the O over I drift ratio. This means the out of plane drift angle divided by in plane drift angle. Okay? So then this 0 means the in plane loading only, and then the 1.5 and 3.0. So then the out of plane drift angle is 3 times in plane drift angle. Okay? And then also this is the axial load ratio, and then these 2 constant axial load ratio, and then we applied varying axial load, like the 0 to 0.2 AGF prime C, then the AG, the gross sectional area of concrete, and F prime C is the compressive strength of concrete. And then here we apply the tensile force, tensile axial load on the column, on the wall. So then the tensile force was defined as the ratio to the tensile force of the reinforcement. So the ACG means the gross sectional area of longitudinal rebars, and Fy is the yield strength of longitudinal rebars. Okay. So we constructed the specimens in several by the different concrete. So then the compressive strength of concrete are different. When from 21.9 to 28.9 MPa. So then when we compare the results of these specimens, then we have to consider the difference between these compressive strength. And then this figure shows the axial load variation. And then here you can see the axial load, and then x-axis indicates the out-of-plane lateral load. So as I showed you, then we considered this type of framing. So then the axial load on the wall should have a relation to the shear force in the beams in the orthogonal direction. So then the axial load is related to the out-of-plane lateral load. So then this is the start of the axial load. This means the service load, and then the axial load is increasing up to the 0.2 AGF prime C, and then the axial load is now constant. And this is the compression side. And the tension side, we have two routes. One is to the zero axial load, and then one is the tensile axial load, defined by the ratio to the tensile force in the reinforcement. And then there are some ways to apply lateral loading. So then we have to define, or we have to decide how we apply the load. So then this is the way we apply the load. This is the starting point, and then first we apply the out-of-plane loading to the up to this point, and then we apply the in-plane load. And then after unloading the out-of-plane load, and then unload the in-plane load. And then we go this way, and this way, and this way, and then go back to the origin. So we call the figure of 8 loading schematic loading path. So there are some ways to apply this type of bidirectional loading, but we chose this type of loading path. And then this is just as I showed you in the previous slide, and then and then, okay. Here, you can see the in-plane direction. The upper figures show the shear strength of the wall in plane shear strength in the in-plane direction. So then this was calculated by the design equation, and also the bottom figures is the fracture strength of the wall. So then the shear strength is smaller than the fracture strength. So then these walls were expected to fail in shear, right? And this is the out-of-plane direction, and then the shear strength is larger than fracture strength. So then these in this direction, the columns were expected to fail in fracture. And this is a loading setup. And then you can see here the specimen, right? And then we use the 6 oil jacks to apply the axial load and then the 2 directional horizontal loads. And then this is the photo of the loading system, and then the axial load applied here, and then the in-plane load and out-of-plane load. And then just to help you understand how we apply the load, please look at this. This is a specimen, and the being applied load. And then here you can see the out-of-plane direction, and then also the in-plane direction load, and then the drift angle relationship, and this is the out-of-plane. And then here you can see the axial load variation, and then this shows the orbit of the in horizontal plane. So now you can see the moving of the specimen. Okay. So, for example, it goes this way and that way. So then the loading system is a little bit complicated, but complicating, and then we control the whole system, and then we realized this type of loading path. And experimental results, as I showed you in the video, so we could have the loading path like this, and then also the axial loading path was realized. And then this is a specimen. It's called the WB15 C20T00. This means that the O over I drift ratio. So the out-of-plane, in-plane drift ratio is 1.5, and the axial load ratio from 0 to 0.20 AG F prime C. And then you can see shear cracks developed and the fracture cracks developed, and then this shows the in-plane lateral load, in-plane drift angle. This figure shows the out-of-plane load, and then the out-of-plane drift angle. Okay, let me show. And then this is when we had the OI drift ratio of 1.5, and then this is this is the after test of the same specimen. So you can see the shear crack here, and then this is the final figure of the specimen. And then this is a different one. The axial load ratio is different. So then we apply the tensile force to this wall. And then here you can see the shear cracks developed, fracture cracks in the out-of-plane direction. And then this is the drift ratio of 0.5%. And then this is after the test. So we had a big shear crack here, and this is the end of the test. And then in this case, we apply the OI drift ratio of 3.0. So then the out-of-plane drift was 3 times the in-plane drift the shear cracks developed and the fracture cracks developed. And then this is the figure at the drift ratio of 0.5%. And then this is after the test. You can see here the shear crack here or this in this direction. So this figure compare the experimental results between three specimens, which had the same out of plane, in plane drift ratio, but the actual load ratio is different. So this red line shows the specimen of 0.2 LGF prime C constant actual load, and this green line shows the actual load ratio being varying between 0 to 0.2, and then the blue line. This is shows when we apply the tensile force in the wall. So as you can see here, when we apply the tensile force in the wall to the wall, then we had a smaller capacity, shear capacity in the in plane direction. So then this y-axis shows the shear capacity, but as I said, the concrete strengths were different between the specimens. So then we standardized the capacity by dividing the capacity by dividing the capacity first by the sectional area of the wall, and then and also by the tensile force, tensile strength of the concrete. So then the y-axis shows the 1.0, 2.0, and then we can now compare those specimens. And then if we have the constant axial load, the capacity is the largest, like this. And then this figure shows the comparison in terms of out of plane, in plane drift ratio. So then we had two types of out of plane, in plane drift ratio. So then the 1.5 and 3.0, and hi. Hi. Well, I almost now approaching the conclusion. Hi. And then in this specimen, the difference is very small. So then in this case, even if we apply the out of plane drift, but that did not influence the capacity of the in-plane capacity of the wall. So okay, let me skip this one. So today I just showed you the experimental results of we conducted on the shear wall specimens, and then we found the bigger difference between the maximum axial load and the minimum axial load was the load lower the maximum load capacity the specimen showed. Okay. So as the design equation suggested, of course, the actual load had the much influence on the capacity in the wall. And then the out-of-plane deformation did not affect in-plane maximum load capacity. But before this project, we conducted another several specimens, and then we found the difference between the in terms of the out-of-plane and then the in-plane direction deformation ratio. And now, with analytical research, we try to figure out the resistance mechanism of the shear walls under in axial loading. So this is the end of my presentation. Thank you very much.
Thank you. Now, the session is open for discussion. One or two questions for limit of time. Yes? Using the microphone there. Thank you.
Okay, is there any reason why you used 1.5 and 3.0 of drift ratios as a variation in this research, and how, as where from those numbers?
Yeah. Yes. So, the shear failure may occur at the drift ratio of 1/200 or 1/250 in the in-plane direction. So then in out-of-plane direction, we assume that we had a moment frame or moment resisting frame. So then 1/200 times 3 is the 3 1/60 or 1/50, right? So then we consider that the maximum or the deformation we usually had. That the deformation we assume that the moment resting frame fails in fracture. Right? So that's why we chose 3. That's a maximum. And then the 1.5 is the 0 and the 3.0. That in between these two numbers. Yeah.
So the time is up, so I would like to go to the next speaker.
So, so for our next presentation, it's jointly developed by Mohammed Al-Tamimi and Professor Gustavo Parra Montesinos from University of Wisconsin at Madison. And so, Gustavo, it looks like you're actually doing the presentation. I thought Mohammed, but yeah, so welcome.
Right. Good morning, everyone. Again, my name is Gustavo Parra Montesinos. I'm a professor at the University of Wisconsin-Madison. This is a research that one of my doctoral students is conducting, Mr. Mohammed Al-Tamimi. Unfortunately, he couldn't come to the ACI convention, so I'm in charge of presenting for him. But as you know, students do the very hard work. If not all, most of the credit goes to him for the work done on this project. So what I will be talking about is on a recent experimental study that we've done at Wisconsin on the seismic behavior of coupling beams, but in particular with some relatively newly developed steel fibers, which we call double hook steel fibers. So first, to put things into context, we're talking about coupling beams, so that means we're talking about structural wall systems. Now, in general, when you have structural walls, let's say mid to high-rise buildings for lateral strength and stiffness, well, walls are actually very restrictive in terms of space usage. So typically, we need to have openings for doors and windows. A common trend in the past few decades in the United States is to use what we call core walls around the core of elevators. So you're going to see, as shown in this photo, well, that we need these openings for, in this case, doors, and that leads then to the wall, rather than being solid, being split into several walls connected then by these short and deep members that we call coupling beams. Now, because of the fact that they are short and deep, these members are subjected to very high shear stresses, and also given the geometry of the coupling beams with respect to the couple wall system, they tend to be subjected to very large rotations, much larger than the rotations the whole wall undergoes during a major earthquake. On the other hand, it is beneficial to have these coupling beams because the system being coupled has a much larger lateral strength and stiffness than the summation of the strength and stiffnesses of the walls being separated because of the coupling action provided by these coupling beams. Now, looking into fiber reinforced concrete within the context of this presentation, we're talking about the use of steel fibers which are mixed with the concrete. So they are relatively short fibers, typically 1.2 to 2.5 inches in length, and they are mixed with the concrete. The idea is to have a random distribution of fibers. As you can see in the photo on the right, well, steel fibers typically have deformations to provide for mechanical anchorage with the concrete. Now, normal fibers, let's say this one with a single hook, are designed to slip rather than to yield as a crack opens. So as a crack opens, any fiber bridging that crack will tend to slip. There will be some local yielding at the ends where the hooks are, but along the length, they are not really expected to yield. Now, there are more modern fibers that have more than one hook, so they have multiple bends at the ends, and these fibers then are designed to then not pull out, but rather than yield along the length, and they have to be made with a very high strength steel, and also they have to be a little bit longer to prevent fracture at relatively small crack width. And on the left, we see a photo of fibers being mixed with concrete. We can actually basically mix these fibers in a ready-mixed concrete plant for large-scale operations. And up to 150 to 200 pounds per cubic yard, which are very large dosages of fibers, we have managed to do that in large-scale operations with a good fiber distribution. Now, I'm going to be referring to a particular type of fiber-reinforced concrete. I mean, we have many types of fibers. We can use them in different amounts, so the performance that you can get could vary significantly. So just to lump this into one particular class, I'm going to be talking about what we call high-performance fiber-reinforced concrete. And the main attribute of these high-performance FRCs is the fact that if you take a sample made of this material, no reinforcing bars, just the fiber-reinforced concrete, and you subject it to direct tension, you're going to have, after first cracking, what we call a hardening or pseudo-strain hardening response. So we see on the top right figure is a plot of tensile stress versus average tensile strain. And what you see, you have cracking, but then you have this hardening response. And then once you have the capacity of the fibers bridging one particular crack reached, then you're going to enter the softening branch of the response. Most fiber-reinforced concretes exhibit a softening response after first cracking, so they don't have this hardening response. Now, one advantage of this hardening response, besides the fact that you have this increase in tensile stress and strain capacity, is that that leads to multiple cracking compared to if you have fiber reinforced concrete without bars, you're going to have a single crack. If you have with reinforcing bars, of course, you have, because of the interaction between the bars and concrete, multiple cracking. But comparing a reinforced concrete member with a high-performance fiber concrete member, you can see that you get a much denser distribution of or network of cracks, which means that you distribute the formations more evenly, so as opposed to just reinforced concrete where you need larger crack width. So basically, you have a lot more tolerance to deformation when you're dealing with these sort of materials. Also, in compression, these materials behave like well-confined concrete because you have the fibers that are restricting or providing lateral restraint against lateral expansion as the concrete reaches the peak or past the peak stress in compression. So that tells us that, well, maybe we can actually reduce the amount of confinement steel or transfer confinement steel when we use these kind of materials, because we start already with a material that has a lot more deformation capacity in compression than plain concrete. Now, in terms of the ACI 318 provisions for design of coupling beams, well, there are various conditions, but the one that is of interest to us in this particular presentation is this one. When we're dealing with coupling beams which have an aspect ratio or span to depth ratio between 2 and 4. Most coupling beams in the United States fall within this category for medium to high-rise buildings designed in the past 20 years or so. Now, if you fall into this category, then you have two options in the ACI code. Either you design the coupling beam with a diagonal reinforcement designed to resist the calculated shear demand, and that comes with very heavy amounts of transfer steel to confine either the diagonal reinforcement cages or the whole coupling beam. Or you use the detailing for a special moment frame beam. Now, if you're dealing with a diagonal reinforced concrete beam, you can design for a shear stress of 10 root of F prime C in PSI. You get 8 root of F prime C if you are dealing with special moment frame beams. Most designers choose to deal with a diagonal reinforced concrete coupling beam because of the higher shear stress. Also, they have or exhibit much better behavior in terms of deformation capacity than a special moment frame beam. Now, as I mentioned a minute ago, well, we need special confinement reinforcement. Is similar to the confinement reinforcement we need for potential yielding regions in a column of a special moment frame. So that actually leads, in combination with the diagonal bars, to severe reinforcement congestion as shown in this photo. So you can get very, very large diameter diagonal bars required to resist the entire shear. Also, the larger the aspect ratio, the shallower the diagonal bars are, and the less efficient they are. So you end up with fairly large areas of diagonal reinforcement. In this particular case, the confinement is provided to the diagonal reinforcement rather than the entire coupling beam. The transfer steel for the coupling beam regions outside of the diagonals, as you can see, is very light. Now, this is a very complicated thing to build, not only because of the diagonal reinforcement cages that intersect in the middle, so they need to, the bars need to be offset, but also you have the transfer steel required, for example, when you're dealing with a special boundary element, which is a fairly closely spaced transfer steel. So you have to thread each bar through the edge or boundary region of the two walls being connected. So this is a very labor-intensive and time-consuming operation. Sometimes these bars are so heavy that you need 2 people and maybe a crane to handle a single bar. So as we can see, these beams behave well, but there is a price you have to pay in the form of the reinforcement congestion, the time associated with the construction of these coupling beams, increase in labor. I'm told by contractors that sometimes the time per floor increases by 1 day if you're dealing with these coupling beams. So you can imagine if you're dealing with a 30, 40-story building, that's quite an increase in construction time. So if you use a material like one of these high-performance fiber concretes, well, maybe we can reduce the transfer steel because the material behaves already like well-confined concrete, but also, well, maybe because of the tensile stress-strain behavior of the material, we can eliminate diagonal bars. And we have shown in the past that that is possible in some cases. We had in the past evaluated 3 types of steel fibers, all 3 hooked, but we call them like single hook because it is just a single hook at the ends. And we've evaluated these fibers in volume fractions between 1 and 1.5%. So all the way to about, so it's between about 130 to 200 pounds per cubic yard. And we've seen that in some cases we can eliminate diagonal reinforcement if we're dealing with aspect ratios, span to depth ratios at least of 2. Now, what we decided to do in this case was to evaluate then these other types of fibers with double hooks with the idea of trying to use lower fiber contents. Also, the larger the fiber in terms of diameter and longer, they are cheaper to be manufactured. So we wanted to see, well, can we come up with a more economical sort of solution. So we tested 12 coupling beams. They were large scale, as I will show, on the large displacement reversals. We look at different aspect ratios ranging between 2 and 3 to cover the typical range of aspect ratios. Shear stresses between 6 and 10. Remember, 10 is the upper limit for a diagonal reinforced concrete coupling beam. This is in terms of square root of FRMC in PSI. We targeted a compressive strength for the concrete of 8,000 PSI. And we evaluated 2 types of double hook steel fibers and in 2 dosages. Now, we didn't try all combinations, so we ended up with 3 steel fiber reinforced concrete or SFRC mixtures that were evaluated. This shows the photos of 2 of the 2 fibers evaluated. You can see now you have 2 hooks here, and you have like a 1.5 hook on the other one. So the left one is called a 5D 6560 fiber. The one on the right is a 4D 8060 fiber, both manufactured by Becker. So we evaluated the 5D, the one on the left, at either 1 or 1.25% by volume. The one on the right at 1.25% by volume. Both fibers have the same length, 2.4 inches. Strength, nominal tensile strength for the left, 335 KSI versus 260 KSI for the one on the right. And the diameter for the one on the right is a little bit smaller, so the aspect ratio is larger for the 4D versus the 5D fibers. I don't mean for you to read these. These are the 12 specimens. They don't follow a particular order because I lumped them into aspect ratios. So that's why we start with 3, 4, 5. Those are aspect ratios of 2. So we have 2, 25, and 3. Fiber type, different types of volume fractions, and shear stress between 6. Most of them were targeted at 8 root of FRMC and some at 10 root of FRMC. I'm just going to focus on 4 coupling beams in the interest of time. The interesting thing is the reinforcement detailing. We tried 2 design schemes in terms of reinforcement. Because these are made of fiber concrete, and typically the walls are made of reinforced concrete, regular concrete. So we're going to have a cold joint, either because we put some sort of mesh or so to block the fiber concrete to go into the wall if we do cast in place, or because we precast the coupling beams. In the lab, we prefabricated the coupling beams. So what you see is the fiber concrete part, the bars stick out, but we evaluated first the use of these U-shaped dowels to increase the shear transfer capacity at the interface. We expect very large rotations at the interface, so we were concerned about having a sliding shear failure that would occur prematurely. And then towards the end of the testing program, we evaluated a similar detail, but without the U-shaped bars, but making sure we have enough longitudinal steel to achieve or provide sufficient shear transfer through shear friction at the interface. So when I say with U-dowels, that means the detailing at the top. If I say without your dowels, that means the detailing at the bottom. So I'm focusing on these 4 coupling beams, 2 aspect ratios, 2.25 and 3. For each aspect ratio, I'm looking at without dowels and with dowels. Target shear stress, in most cases, 8 root of F prime C. In one of the coupling beams here, we have 10 root of F prime C. And volume fraction, 3 out of 4, 125% versus 1%. I just mentioned that we prefabricated these, so we started with the reinforcement cage. Then we cast the fiber concrete for the coupling beam. Then we put it in place. We have 2 massive, very large stiff blocks simulating the edges of the walls, the wall being connected. Then we cast the regular concrete for the walls. The way we tested this, for convenience, we rotated the specimen 90 degrees so that the coupling beam, instead of being horizontal, it was vertical, as you can see here. Now, what we wanted to do, or we needed to do, was to make sure the 2 walls being coupled, in this case, these 2 horizontal blocks, were fairly parallel, or almost parallel during the entire loading regime. So we have these steel links that ensure that the 2 blocks were basically parallel. We apply lateral displacements at the top, horizontally, back and forth. And drift, that means the relative displacement of the top of the coupling beam versus the bottom. If I talk about drift ratio, that would be the relative displacement divided by the total coupling beam length. One important thing is that these links also provided some degree of actual restraint, which will occur in a real building because you have the walls that provide some restraint against the coupling beam expansion and also the floor slabs. And at the bottom, I'm showing a photo of the specimen, so the coupling beam with the 2 blocks and the hydraulic actuator to provide lateral displacement. We had 2 loading protocols. So for most coupling beams, we had 1 cycle at each drift level. We started with basically 0.25%, and then increased 0.5%, 1%, so on, until failure. And then for the last few specimens, we did 2 cycles at each drift level to evaluate the effect of repeated cycles at each drift and basically stiffness and strength retention during repeated cycles. We also did some material tests to evaluate the performance of the materials. One of those tests was a direct tension test of notch specimens. Of interest here, this is the tensile stress versus crack width obtained for these prisms under direct tension, which were notched. This is normalized by square root of F prime C. And what you can see here is 2 out of the 3 mixes, the ones with 1.25% volume fraction, they had a peak tensile stress after first cracking that was greater than the first cracking stress. So this is kind of the condition for string hardening or a high performance fiber reinforced concrete. We also conducted ASTM 1609 tests. We have also a hardening response for these tests after first cracking. And this is normalized by the first cracking strength. So in some cases, we reach post-peak stress, almost 40% the first cracking stress. Looking into the hysteresis, this is normalized shear stress versus drift response. Well, as you can see, if you pay attention to the y-axis, this is shear stresses over 8 root of F prime C. Drift at 20% strength decay. Well, in this case, in the negative direction, it went all the way to 8%. For the other pair of specimens, a similar behavior. One had lower shear stresses than the other one. An important thing here is that, red and blue, one with dowels, one without, black and blue, one with dowels, one without dowels, a very similar behavior in terms of drift capacity. So that means that we can simplify the reinforcement, remove the dowels, and still achieve good performance. Summary of the test results, we can get a fairly stable hysteresis response at high shear stresses for all the tests that range between 7.1 and 10.8 root of F prime C. because of the actual restraint, we got actual compressive forces developing the coupling beams that were on average about 10% of the product of F prime C times the gross area. We got at least 5% drift ratio before we got 20% strength decay. And the behavior was dominated by flexure until the very end where, for the case of the U-dowels, the coupling beam started having quite a bit of sliding at this section at the end of the U-dowels. So photos showing the damage progress up to 4% drift in this case. As you can see, beyond 2%, pretty much all the cracking had developed. As I mentioned earlier, because of the material we use, we got a fairly dense cracking distribution. And at the end, at larger drift, what we had was quite a bit of damage at both ends of the coupling beam. In terms of effective stiffness at first yield that you can use for an elastic analysis, well, we don't have diagonal reinforcement here, so our effective stiffness are about 2/3 on average of the effective stiffness recommended in Appendix A of the ACI code. Energy dissipation is similar to that of well-detailed diagonal reinforced coupling beams. Whether you had dowels or not, it didn't matter. This is actually a normalized energy dissipation, so basically normalized by an equivalent elastoplastic system. So you get values roughly about 40%, except for this red specimen. This one had the lower shear stresses out of the four I mentioned. So you get quite a bit of energy dissipation capacity, over 20% higher than for the other three. Before I conclude, I wanted to show these two plots. This is basically tensile strengths measured in the transfer steel along the length of the beam. So what we have here horizontally is the location. So you have the left end of the coupling beam, the right end of the coupling beam, and then the midspan region. At the ends is where you have more confinement reinforcement. In the middle, you don't have any special type of transfer steel. In the y-axis, what we have is a normalized strain, normalized by the yield strength of the transfer steel. In all cases, that ratio was less than 1. So that means all the transfer steel remain elastic, even in the plastic hinge regions. I should mention that for the middle portion, we were able to count on 4 square root of F prime C in PSI of contribution of the fiber reinforced concrete. So typically, in beams of special moment frames, we use 0 for VC. So we use 4 root of F prime C, so that means we didn't need as many hoops in the middle region, and still with that, we didn't have any yielding. So just to conclude, well, I've shown that if we use a strain hardening fiber reinforced concrete in coupling beams with aspect ratio of at least 2, we can achieve a stable hysteresis dominated by flexural deformations, even for cases of coupling beams subjected to shear stresses as high as 10 root of F prime C megapascals. We achieved a drift of at least 5% before we got a 20% strength decay. We only needed column type confinement reinforcement at the ends rather than over the entire coupling beam as you require for diagonal reinforced coupling beams. As I just mentioned, we can rely on a contribution of the fiber concrete to shear, the so-called V sub C term for use in the middle regions of the coupling beam was 4 root of F prime C. And whether you have U-dowels or not at the ends, it seems that that did not lead to any meaningful difference in behavior. So as long as you have enough longitudinal steel crossing the interface, or the beam ends or the beam wall interface, to have enough shear friction, you should be fine in terms of not having any sort of sliding failure prematurely. With this, I conclude. I want to thank Becker Corporation for providing financial support for this research, as well as the University of Wisconsin-Madison. Thank you.
Very good. Yeah, thank you, Gustavo. Unfortunately, I think in the interest of time, we're a little bit behind, so I'm going to have to defer having questions. But if you get a chance to talk to Professor Gustavo, please, do. We want to thank you for your contribution, so we have a small gift for you joining today.
Thank you. Really appreciate it. Thank you all.
Also, presentation
The next speaker is Professor Sam Kono. He is a professor of the Tokyo Tech and a graduate from Kyoto University. And he also received a PhD from University of Illinois at Champaign, Alabama. His research interests cover seismic assessment, seismic retrofit, performance-based design, damage control system, precast and pre-stressed concrete, and high-performance concrete. Please, Professor Kono.
Okay. Thank you very much, Johanna-san. Okay. My name is Sam Kono from the Tokyo Tech, and I'm very glad to come here and make a presentation. Oh, like this. And then this is some kind of effort we are trying to do, especially in the building structures. Okay. And then the seismic design for buildings, main in Japan, what's happening after the 81. We make a big revision in 81. The revision up to that point, this one, allowable stress design. Okay. And so until the 81, we are designing the building for the intermediate earthquake and then using the allowable stress and then stopped it. And so we don't know how it's going to fail under the large earthquakes. But 68, 78, lots of earthquake, and then the building collapsed, and people started to worry. Why? Because we are not designing for the ultimate conditions. And so the Japanese society decided, oh, we need to design for the ultimate conditions, for the large earthquake. And so only for the superstructures or above the ground, we started to design for this ultimate condition. And we check the lateral load carrying capacity of the building. Okay. And then that time we didn't do anything for the ground or foundation. And so piles, foundation beams, we didn't see, or people didn't see any big damage. And so they decided, oh, we don't do anything about the foundations. So there's no requirement for the second level design at that time. Since then, it's kept the same. Although we started to see some damage, and then, oh, probably it's time to design for the large earthquake, even for the foundations. And then this is Kobe earthquake, and then after those 81 earthquake, we didn't see very much like a real collapse. And then if you follow the new design code, and then is it perfect? It's not perfect. But for example, this like even if you follow the new design code, the new means the 81 code, and then we still have the damage for the soft storage. And if you have a large like shovel in the backside of the building, for example, and then there's a torsional effect, and still you have a damage to these columns because of the enforced displacement. And then also this is from the Komuro-san sitting there. And then this is 81 is the year of the Earth, those new codes. After that one, we didn't see very much like a collapse of severe damage to the buildings. But before that one, you see the really large like a collapse, the severe damage is happening. So we are saying, oh, that's important to see the assessment of the buildings for the seismicity and also the seismic retrofit. And then the Tohoku earthquake, there like 2011, and tsunami is one of the big things. But for the building side, due to the shaking, what we are going to see is this is the like a gymnasium of the school. People are using those buildings for the evacuations. And so if you cannot use your own big, like residential buildings, people go to these places, gymnasium, and then spend the time. But if you have a damage like this one, then everything is shut down, and you cannot use those places as a refugee camp. That's really sad. And so this is one of the big things. And then these like non-structural walls, especially, so until like 95 or even 2000. And then the structural engineers, professor saying, oh, your building is quite safe. Nothing bad. It's okay. Because this is non-structural. But people started to feel, no, it's not quite right. We cannot live. With this big damage, and then you cannot use that building. And so people started to feel, oh, probably the safety is not the only issue. And that's happening also in the States or New Zealand, the same way, okay? Resiliency is one of the big issues. And so those are the things. And then the third one here is the foundation, especially the piles. And then some people feel or know those piles are damaged, even in 95 earthquake, but people didn't see, or I didn't even see them because it's not on the, we are not people, we are not seeing. And then the media doesn't know, professor doesn't know, unless the building is really like a tilted. Okay? But for the superstructure is good and something is bad, and so they dig the ground and they found out, oh, it failed like this one. And then for people working on these like foundations or soils, they knew from the 95, oh, the piles are getting damaged. Why? Why? Because we are not designing. Okay? And so here the safety is still the most critical issues. Even for Kumamoto, for 2011, like Tohoku 95, Kobe. It's really like still the safety is big issues. But people are seeing, oh, resiliency. Okay? And so the new code is, our new code means like 81 code. They're securing your building is safe, no collapse. But they are not assuring like resiliency at all. That's what people are seeing these days. But that's probably not only in Japan, but which is happening outside of Japan too. And then just example for the 2011 Kumamoto earthquake. And then what you're seeing is these buildings. And these buildings, after earthquake, the superstructure is safe, but it's kind of tilted. And then people wonder what happened. So they dug out this foundation and then found out, oh, the pile is really damaged. Okay? And then so it's time. It's time to work on the pile for the large earthquake. And those are the really big motivations. And then what piles we are using, like timber, this is very old. Okay? And also steel. And the steel piles are mainly used for the bridges or like civil type of thing. And we are not using very many things for the building structures. And then what do we use for the building structures? Mainly we have, the first one is precast concrete piles. We make this in the centrifuge. And so it's a spun concrete. And then they started these things for the like a 60 megapascal, 70 megapascal concrete. But these days, the main product is 105 megapascal or 125 megapascal. And then a few of them is this one is pre-stressed high-strength concrete pile. And then if you add the mild steel in the longitudinal direction, it's what we call PRC, pre-stressed reinforced concrete piles. And then there's a CFSD pile as well. And this is hollow. Everything is hollow because it's spun concrete in the centrifugal fabrication. And so this is one of the big things. Probably you don't see, as far as I know, I don't see them in States or Europe. But we use it here in Japan as well as the Taiwan, probably in China. Because especially this PHC price is low. And so for the building up to the 10 stories, probably the constructors or designers want to use this PHC because of the price. Okay? And then what's going to happen for the large scale or the high-rise building? They use the reinforced concrete piles or CFSD piles. And so this CFSD piles, for example, this red one is the shell, okay? And then the size is, it says like 700 mil to 2.5 meter. That's very large. And then but the thickness of the steel is like a 12 mil or 60 mil. And that makes D/T ratio, that is the diameter to thickness ratio of the steel, is 100 to 200. That's very large. So that means like this is really skinny, like a shell is around the concrete. There's a lot of study on the CFSD column, and then those D/T ratio is 30 to 50. And so you have a really large, thick, like a steel, and then steel can hold the compression a lot. But for these skinny things, you cannot expect the development of the full capacity, plastic capacity. Okay. And then this is example of the spun concrete pipe. And then there's like a PHC, PRC, CFSD. Okay. And then here, the really typical one is 105 megapascal, hollow section. D/T is around 60 to 100. And then the diameter itself is 300 to 1200 mil. And so they are used for the up to 10-story building. Okay. And then for the PHC, you don't see any shear rebars. These like spirals are for the assemblage purpose. PRC, they add longitudinal as well as spirals. And then you can expect a little bit like a shear confining effect. And then CFSD, there's no rebars at all. And they never tested the pile under the large, like axial load. And so this horizontal one is axial load ratio, probably. This is the axial load itself. And then the vertical one is moment. And then the pile companies tested about this range. But we found out those like piles are used under the larger axial load. Like axial load ratio is 0.4 or 0.45. That's still common under the large earthquake. And also they never tested the pile under the intention. And so we decided, oh, probably we need to do it. And this is the test setup. And only, this is like simply supported 4-point bend test. But to apply the load, we put this like a frame. And so this is only for the frame to apply the axial load horizontally. And then the hydraulic jack is hidden in here. And the total is 2,000 tons in axial load. Okay. First one is PHC, and then this one is under tension. Yeah, of course, like it's ductile. And then this is under the axial load ratio 0.42. And then up to this point, and then it's really explosive. This is the first one. Under the tension, it's ductile, it's okay. And then I used to have a video, but I don't have it. It explodes. It's really scary. Okay. And then usually we go and take a look, and then the students draw the line, and then those like industry people said, never do it. It explodes. And they really exploded. And then the PRC, why the PRC? Because you add the mile rebars, and then you increase the load capacity a little bit. And also probably the ductility. That's what the people expected. And then under this, again, like a tensile axial load is ductile. Or up to like 15%, 20%, its behavior is okay. But like if you apply the axial load ratio like 40%, again, it's exploded. And so those shear rebars or mile rebars doesn't work at all. Its behavior is about the same with PHC, PRC. Both of them are very, very like brittle. And then same, and I don't have a video, sorry. And then the CFST, the PHC, PRC, they use mainly at the very deep at the soil. And then if you have a large moment at the top, the designers usually use this like CFST pipe on the top of them by splicing the pipe. Okay. So they're kind of expecting the capacity as well as some deformation capacity. Yeah, it's much better than the PHC, PRC. This is 10% of the actual load ratio. This is ductile, and I have a dissipate large amount of energy. This one, what happened? It buckles, and then the concrete inside probably crushed at the same time. And so it's not as ductile as you think. Okay, and then until now, people are designing up to this point like allows this design. But even if you apply the ultimate capacities, can you make sure like it's ductile after that one? But no, it's not as ductile because DO2 ratio is 60 to 100, and it's hollow and the high strength and no rebars, and then once it crushed, it drops. And so the behavior is not as good as that. This is happening under even like 18% of the actual load ratio. So it's not very high. We also tested 25% or 30% of the actual load ratio, and then the behavior is more brittle. Yeah, this is like a buckling happening. And then once it's buckled, this portion is very brittle, and then the next you pull it, and then it's fractured. Yeah, so for this is moment capacity. For the moment capacity, if you use this cowl is like a plain section being plain, and then the perfect bond between concrete and steel, bond, those like PT tendon, then you can predict it's okay. Okay, and then we assuming, I think we are assuming like 0.3% of the ultimate conditions, and then yes, under that condition, the capacity can be predicted kind of safely. Although like see that scatter is large, probably because of the shrinkage. Because after the centrifuge, we put them into the autoclave, and then the probably shrinkage around the rebars is large, and so the scatter of this PRC is much larger than PHC. And this is for the precast CFST, so it's hollow. Okay, we are using the same method for the section analysis by limiting the strain of the concrete, and then the ultimate condition is we are using right now is 0.4%. And then if you apply a high actual load, then these things is below 1. Now that's kind of scary because we are expecting much better behavior for the CFST. And so we are limiting the ultimate this strain to the 0.3 under the large axial force. Large axial force plus like if DC over TC is about the same thing with thickness to the radius of the thickness ratio for the concrete part. Okay. And so those numbers are large means it's thinner. Again, like it's unstable, and so that you cannot attain this capacity. And so we changed by limiting these things. Okay. We are probably supposed to consider those like thickness rate, thickness effect explicitly. Time. How much? And then this one is like a casting place CFST. Again, like a D over T ratio is 100 to 200. Their main product is like 140 to 160. And then somebody checked the design condition, and then they see this like a unreinforced like CFST is used under the up to 40% of actual load ratio. If you put the longitudinal rebars, and then they're using up to like a 50%. That's very, very large. And then again, like if you applied axial load. This is like a 1.2 meter diameter, so 4 feet, very large. And then we applied almost like a 2,000 ton axial load. This is fabrication. And then under the compression, it buckled. Probably you cannot see. This is buckled. And after that one, you press it and then it's extended, it fractures like this. And this zigzag is due to the fabrication. They are using the inside of the ribs for the shear key. Okay. And these things with stress concentration happens, and so the fracture happens like this much. Okay. So even for the CFSD, like up to the failure, it's fine, but the failure happens the negative side because it's compressed. This is compression, and then it's that kind of ductile even after 40% of axial ratio. And then if you pull it, and then it fractures. Okay, and so those are something that people are not expecting for the casting plate CFSD piles. People assume in both directions it's very ductile and countable, but probably it's not. And then again, like you use a texture analysis. Yeah, it's okay. Rather, like many of them we are kind of undershooting because epsilon Cu is limited to 0.3. That is very like a small. In the test, the maximum is attained around like a 0.45 or 50.5% of the strain at the compression fiber. But we are limiting to the 0.3, and so for sure, like it's kind of conservative. And probably the next phase is we need to consider the deformation. How much the deformation capacity we have is a big issue. And this is again from like Komuro-san and Taisei Corporation provided us these things. This is reinforced concrete piles applied like a 40% or 50% of axial load, and then the cyclic testing, and then this is 0.5. It's really dropped, and so they decided, oh, probably we want to go to the 0.6. But instead of going 0.6, they decided to do 0.4. Even for 0.4, like a degradation is so quick. And then partly because of the crushing and also these vertical cracking due to the large axial force plus like a shear. And so it's kind of easy problem because people have worked on the columns, for example, and the CFSD. There are lots of like test results, but not for this like a particular one because these are a little bit different from the columns. As I said, like a thinner or a high strength, so it's hollow, or sometimes like this CFSD D over T ratio is so large. And so you can expect some similar behavior, but like a existing code equation does not cover the behavior of these things. And so you need to test it first, see the behavior and the failure mode, and then formulate them. Those are very important issues. The same for the RC piles. And then this is just a summary of the pile itself. And then there's also shear problem, although probably I'm just skipping them. And the failure mode is different. And then the pile is not the only issue. This is pile. And then this is simulating, this is beam, and this is supposed to be column. And then this is pile cap behavior is another issue. And so there's a shear failure as well as some kind of a flexure failure at the pile head. And then which portion you are going to make the plastic hinge is a big issue. Okay, type. Okay. And then those pile cap, and there is some like a revision made in the AIJ code, but we are still working on it. Okay. This is some area. Okay. Thank you very much.
Excuse me, a quick question.
Okay.
So do you think of the concrete piles failure, was there any lateral spreading that happened in the soil and that might have increased on raised length of the pier and that caused a failure like you have shown in pictures?
Sorry, I didn't understand. Sorry, I didn't understand the question.
So did you notice any kind of a lateral spreading of soil?
Soil conditions.
Yeah. So the way the drill piers are failing, they're failing as if there's a long unbraced length of the column, right? So was there any, when the geotech investigated after the seismic, did they notice any kind of lateral spread?
Some of the building, yes, due to the side spread of those soil condition, the pile failed, but not all of them. Not all of them. And the couple of buildings which had the damage of the pile, not due to the side flow of the soil, but just due to the probably shaking of things. Thank you very much for asking.
Is there any chance for questions? Okay, thank you very much. Very quickly. About your building code, something so clear to me. You are saying it's going to change. But it's going to change in which direction? In the sense that you are asking some ductility for the piles? Or you are designing the foundation with over strength? So this is quite crucial.
Right now, building is lower than 60 meters, and then you try to design for the foundation structures for the large earthquake. And we said design for the large earthquake. And then probably in the future, we need to design which portion have a plastic hinge. Right now, you fix the foundation and then do the push-over analysis or something, and then you.
But you do it with over strength or not? Because if you do it over strength, then you don't need a hinge.
We started to think about a whole building, including the foundations need to be included for the analysis. But it's a big discussion because of the soil conditions. And soil people said, no, your spring is wrong. And they use this spring for the static condition, they use this one for the dynamic condition, but nobody knows which spring is right. And so once you give it the spring property or something, and then the whole building can be analyzed with the foundations. And then probably you can make a more optimum or proper collapse mechanism.
Okay.
That's possible.
Okay.
Thank you.
Thank you. Time is up. Thank you. Some visitors will give you.
Thank you very much.
Thanks, Mike. I trying to make time here. First of all, I'd like to acknowledge some very hardworking graduate students. Esan Buffet is sitting here in the background, and Ariel. They're both actually going to end up working for WJNE or are working with WJNE already. Hamid is our machine learning wizard, and he is now working at Dagan Kolb Engineers. They had a lot to do with that work on this presentation. So the topic I'm going to talk to you about today is related to confinement regions and columns. In the way that the ACI code is set right now is one is required to provide special confinement over areas where one might expect plastic hinge lengths, plastic hinges to occur. The internet is not helping. There you go. And that's at the end of columns. So what we're trying to do with this work is to evaluate what is in the ACI code maybe a little bit more carefully and develop recommendations. There are things that we can do now that were not possible when these original recommendations were developed that might help provide a little bit more clarity. So the recommendation, as best as we can tell, traces back to the 1990s. There was work by Professor Park and was followed up by a discussion by Professor Melly and others where they looked at damage They were focused more on a couple of different approaches to say where you need special confinement in a column. One way to do it is to say that you can use equations for protoplasticity. The other one is just to look at damage in photographs and make a recommendation based on that. So Professor Park made a simple recommendation where he said that length of confinement should be proportional to the axial load, because he saw some damage in columns with high axial loads where that damage region extended further. Professor Maley went a step further. He used a slightly larger data set, and he linked it both to axial load and the shear span to depth ratio. So I was mentioning there are things that we can do now that are a little bit different. We have a database that's been developed by, originally by Peer, enhanced by Committee 369 of ACI. And that allows us to look not only at what is outside of the column, but what is inside of the columns. There are a number of parameters that we know. We have a data set of columns where we know axial loads, we know transverse reinforcement ratios, we know shear span to depth ratios. We know a lot of information about the makeup and the testing of these columns. And in addition to that, we can go and look at those reports and extract images and utilize image processing techniques. So what we try to do is combine the two sources of information to do a more comprehensive analysis and say where, if we can tell what that spread of damage is in an image, how does it relate to the properties, configuration, and the loading protocol that was done for the columns. So, the other thing that we've done is, since we have a data set of 700 columns, is we can begin to utilize techniques from data analytics and machine learning. They begin to tell a story of the composition of that data set. As I was saying, there are techniques that we can use about data analytics because it really, at the end, it's about matching an observable pattern of damage with some set of characteristics. And to do that, we need to understand how the database is made up and what may be some parameters that drive the behavior of these columns in the damage. Okay. Oh,
That application isn't active. Yeah. There you go.
So the first question that came to mind is what were the damage metrics? And Essen and Ariel, who looked at this closely, looked at a couple of different possible metrics. So one is confined to spalling and is shown in the red, and it's a lower distance, smaller distance. And the other one is in general, how far up the column are we going to get some tracking and indication of damage of the stress. So there are two. So you begin by questioning everything. How do you measure? What should that confined length be? And how do you go about measuring? To be honest, after we look at these, you can see there's substantially larger distances when it comes to damage in general. And I think that profession maybe is not ready to go that far in terms of providing confinement. So we ended up working with the shorter and say we need to provide confinement. Maybe we're going to focus on what the spalling length may be. There's a second question that immediately comes to mind is whether this damage is proportional to deformation, whether it's going to get worse the further out you push it. So we did a couple of different evaluations, one in which we took studies where people had taken pictures at different levels of deformation. And then we did a separate analysis where we just took the last image of the set, where all the damage had come to take place. And what we found is that the damage pattern establishes itself early on, and it sort of becomes worse in terms of the cracks get wider, the spalling gets to be more evident, but the length of where it occurs really doesn't change. So whether you're dealing with a smaller or larger deformation, your distance alone really doesn't matter. And so at that point, rather than deal with a broader set of images at different drift ratios, we just began to focus on the images at the end of the test, because they were going to tell us essentially it was the same damage length as it would be early on. It was just much more evident in those images. And so we did a first statistical analysis with all the parameters in the database, in the column database. We tied the images and the lengths that were measured from the images to the database. As you see, Ehsan and them tried many different combinations of column parameters to find out what they would, how they would match. And if you look here in the very top corner, coefficient of variation for the Park and Mealy equation, they do a pretty decent job, about 0.4, 0.49 for Park. And no matter what we tried, we couldn't do any better. So we had to go back and tell Jack Mealy, man, you're really, really good at your job. We already knew that. Well, here's one more point that proves it. You did this with about 15 or 20 columns. We didn't go in depth into as many data points as we did, and you came up with something that we can't do any better, right? So that got us a little bit thinking. And there's been a lot of work that we've been doing with machine learning around the column data set. And we've used different techniques to visualize and to understand the makeup of the data set and to begin to tie or group columns in terms of behavior. And we thought that might be a helpful thing. So what you see here is a couple of things combined. First of all, we use a technique to reduce dimensions. When you have many parameters in a database, it's very difficult to see the effect of each parameter individually. So there's a technique here that sort of reduces that multidimensional problem into a two-dimensional problem and puts it in a graph. And then we use a technique that is called Gaussian mixture model to try to lump those columns into likewise sets. And so what you're seeing there is an image that has many colors and some dots in it. Wherever in the image you see similar colors, the columns themselves are similar. And the dots tend to group in different areas of the image, so those become columns that have common characteristics, that have some commonality to them in their behavior. And so when Hamid first showed me this, like, this is great stuff from data analytics, but an engineer wouldn't be able to make sense of it. Let's go and look at those clusters. So those dots we accumulate in clusters and see how those clusters are made up, because engineers will sure as heck understand that. And he came up with this table, and for each cluster he identified a number of different characteristics. What we found was interesting is you see behaviors here that are cluster. I think the most significant trend that you will see, you'll see wide ranges in axial load, you'll see ranges in transverse reinforcement, but they tend to lump in terms of A to D ratio, shear span to depth ratio. So this begins to tell us a story where the shear span to depth ratio becomes an important parameter in defining the behavior of those columns. So upon our first failure of looking at this data set and not having it work pretty well, then we took a closer look and we said, let's break these into bins in which we separate them by A to D ratio. This is kind of what the machine learning techniques were advising us to do. And then separate them again in terms of axial load ratio and columns that have low axial load and high axial load. And then we began to see some trends emerge that were not visible when you consider the entire set as a whole. So you see here there are three regions of analysis that we identified: short columns, what we call intermediate, these are typical building columns. And then on the right-hand side, we have the slender columns. We call those bridge columns, which tend to have very large A to D ratios. And then we broke those into high axial loads for the filled symbols in low axial loads for the hollow symbols. And what we see from this trend is, as we look across, like the broken lines are the low axial load columns, you could almost draw a line across the entire set. So when columns have low axial load ratios, there's really no point. Just take the average, and the average will do, because it seems that all other parameters are not affecting what that confinement length would be. But when you look at the solid lines, the blue line and the solid red line and solid black line, a different story begins to emerge. First of all, for the black line in the short columns, it seems to be telling that the dots are all over the place and that you're better off confining over the entire length of the column. When you look at intermediate and slender columns, I think there comes a picture that says there is an increasing length with axial load and span to depth ratio. So Esan went back and did lots and lots of statistical analysis. And I'm not going to use the pointer because every time I click on the pointer, I'm beginning to notice that the image comes up. But now, as I mentioned before, we had coefficients of variation for the Park and Bailey around 0.39. This is just for a subset of data, so it does a little bit better. But now, when we begin to focus on the intermediate in slender columns with high axial load, then we can tailor equations that do a much better job in terms of coefficient of variation. So what we find is there's a trend that says we need to separate the columns because the behaviors are different, and then the confinement lengths are going to have to be different to address that. We also found that there's an effect of the longitudinal reinforcement ratio of all the things that are inside the column. This one seems to matter the most, and it kind of makes sense. Again, we're focusing on slender columns and intermediate columns with high axial load. Those seems to be the ones that matter. And if you look at that line, the orange line with the decreasing trend is the short columns that says, don't worry about reinforcement, longitudinal reinforcement ratio in short columns. It has no rhyme or reason. But for the other two, you do see the blue line and the red line, they have positive slope that are telling you that longitudinal reinforcement ratio is having an effect on intermediate and slender columns. So reinforcing the idea that the columns belong in the different buckets. So based on that, we came up with some simple recommendations. On the low is the same graph that we had before. For low axial load columns, we said it really doesn't matter. The one thing that we know is the ACI code today tells us to use 1 times the column dimension. If you want to be safe and move to a mean plus 1 standard deviation, you need to increase to 1.5 column dimensions. But other than that, there's no point in changing anything else. When you get into the high axial load for the short columns, our recommendation is that you confine over the full length, just based on the scatter of the data and what we saw. And for intermediate and slender columns, Esan developed an equation that is a function of axial load and A to D ratio. We could also put in there an equation that accounts for longitudinal reinforcement ratio. We figured that the improvement in precision was not all that better. You see a summary here of mean, standard deviations, and coefficients of variation for this column subset. Again, the work that Jack did in the 90s is great. We were only able to improve it a little bit by going through all this process of analysis. So here I'm going in the beginning to wrap up. There's a question, the last question that I want to address today is, how does this relate to design recommendations? In the ACI code, there are two criteria for that confined length. The first one has to do or is based on the column dimension itself, how wide or is the column B or H, if you wish, the cross-section dimensions. The second one is based on column height. It says that you shall confine over 1/6 of the column height. And so you have those two criteria in these two graphs here, left and right. The first one is the column size, and the second one is the column dimension. And we looked at different sets of data for short columns in the circle, intermediate, and slender columns. In different recommendations, so this solid line is what the ACI code proposes today. And the problem with that is you get a lot of dots over the line, and dots over the line are not good. That's kind of a bad thing. And so if we become more conservative, these lines are criteria that are more restrictive, whether you do it 1.5 or 2 times the column depth. Then you begin to include more points under the line, which means that the points are moving to the conservative side as you become providing a more conservative provision. So here we have different cases. And for the columns low axial load, all of the hollow signs fall underneath the ACI line. There's maybe just a few that don't. But when you start to consider high axial load cases, a lot of them do fall above the line. Especially like if you consider these circles that are the short columns, you almost have to draw a vertical line to get them to fit under the line. So that's why we recommend that you confine over the entire length of the column in order to keep these in check. For the intermediate and slender columns, those are slender are in the red triangles, intermediate are in the blue. Intermediate you can cover with the red line, and slender columns you can cover with the blue line. So we come up with criteria that are a little bit more conservative for slender columns than intermediate columns. And like I said, for short columns, we say confine over the full height. This is the same graph, but now in terms of column height and the fraction of column height, it's the same idea. This is the ACI code today. So all the points above that line are points where that spalling length exceeded the requirement in ACI. And of course, if you look at those short columns, they stick out, they're a concern. So we came up with different coefficients. The ACI code today says you shall use 1/6. We are recommending higher values, 1/3 and 1/5 for intermediate and slender columns. This I'm not going to dwell too much. Is just illustrating when is it that column height controls over section dimension. In the ACI code, this provision really meant that column height would control for very slender columns, and it wouldn't control for intermediate and short columns. And that really hasn't changed for double curvatures, columns with double curvature, because we're increasing both the requirement for in terms of column height and column cross section. So that's not much of a change. It does have more of an impact on single curvature columns, although those are not very commonly found in buildings. And this is a comparison of where the ACI is today in what is being recommended. Proposed criteria for columns of different heights. So you have a 10-foot column on the left, 15 column on the right. And here each column corresponds to a different column cross-section. So going from 16 inches to 36 inches. So for the 10-foot column, all of these fall in the intermediate category. The last two columns fall in the short category. Because the column is so big that for a 10-foot height, it actually falls an A to D ratio below 3, assuming that you are in low curvature. In the slender columns, you have very slender for skinny sections. When you get right around 24 inches or less, they begin to qualify as intermediate columns in our criteria. And what I want to call your attention, here's the ratio of what was in the ACI and what is being proposed now. We're recommending an increase. Unsurprisingly, everybody says, you seldom find research papers saying that the ACI code is too conservative, right? But really, this reflects a change maybe from looking at the mean of a photograph to actually doing a little bit of the statistics and saying, we're recommending a mean plus 1 standard deviation. And the effect on columns with low axial load is about 25% decrease in the confinement length as we become more conservative as a result of bringing statistics into the discussion. Where it makes the most difference, you will see it certainly in the short columns with high axial load, you're confining over the entire length, so that's a big increase over what the ACI does today. If the columns are intermediate, not as short, it's still a significant increase. We're telling you to confine over twice the length that is done today, but not 4 times, not as significant. Summary recommendations, we found, again, I think this is in agreement with the findings by Jack Maley, that the parameters that matter the most are axial load and the span to depth ratio, to a lesser extent, the longitudinal reinforcement ratio. For columns with low axial loads, there's really not a significant effect of any parameter. So if you try to tackle those, all you're going to do is add scatter to your statistical analysis. There's no significant help on those. You might as well just take an average and go with that, and that's the best approach, we think, for this data set. When you get into the high axial load ratio, then shear span to depth ratio, longitudinal reinforcement ratio were significant parameters. Short columns showed a great deal of scatter. That's part of the problem. For short columns with high axial load, we're recommending that you confine over the full length. And for intermediate and damaged columns, we came up with a new proposal that says you shall do a more conservative approach, a larger confinement length, if you will. I think that's my last slide. Again, under this criteria, we found the ACI confinement length requirements today to be on the unconservative side. In much more so, I think the bigger concern are the columns with high axial load ratios and short span to depth ratios. Thank you, and I apologize for all the technical difficulties.
Thank you. Much appreciated. Thanks for persevering here. We are a little bit over time, but maybe one question if anybody has one.
Thank you very much. We have a few questions about short ones. Regarding that database, maybe you said they all fail in the same way, I assume. If you can just confirm that if they were different failure modes. And if something regarding the lapping, I mean, they were all lapping in the same way in the critical region, so you do notice any influence of different lap lengths, or if this was accounted to the database?
For this, so the database has, to answer your second question first, has columns with lap splices in them. It has columns that don't have lap splices.
Lap.
Yeah, so this analysis is limited to columns without lap splices, or specimens without lap splices. We didn't go in that direction. You said in terms of failure mode, the database does include failure mode of the column, and we've done a lot of work with data analytics. We've come up with decision trees. If you look up Hamid on GitHub, he actually has a tool where you punch in the parameters for your column configuration, and it gives you what a machine learning tool would think is the best, a neural network would think is the best estimate of the failure mode.
How can a recommendation cover different failure modes? This is not correct. So if you are noticing things which are different, why you are recommending the same thing if what you have here can relate different failure modes? Because
first of all, these recommendations are for special and intermediate moment frames, new construction. So if you look at the beginning, I kind of neglected to mention in the haste of dealing with all the windows over and over, we focus on flexure shear and flexure critical columns. Because you won't find shear critical columns in new construction. That's just not going to happen. Our intent or our thought is this you can apply to new construction, this you can apply to retrofits as well, right? But the idea is that if you retrofit a column, and if you attended our 369 meeting, there was a presentation which dealt a little bit with this. Idea as you retrofit a column, you take away the lap splice and you take away the shear failures, and you transform your column into a flexure dominated column. Maybe flexure shear, maybe flexure by itself, but nonetheless a member with flexure control.
Very lastly, 10 seconds. You're proposing a statistical analysis saying you pick the mean plus the deviation. You are right?
Right.
Are you relating this to targeting any probability of failure, or is it just, you say, mean plus one time?
It's just a mean plus. So the problem is we had 76 images, right? So we've done work on the full column database where we've done Monte Carlo simulations and we talk about probabilities of failure. All of that is possible when you have larger number of images. But with the size of the data set that we have, we just don't think it's statistically meaningful to go to that level of detail.
Thank you.
Good questions. Thank you.